And so this video is going to be focusing on rotational dynamics. So we're going to put the last two videos together in the culminating kind of topic here, which will be rotational dynamics, right? So in Unit 2, you think back way back when, we learned that forces cause changes in motion because they cause the object to accelerate, and we use the equation F equals ma to calculate that. So torque, remember, is the rotational equivalent of force. So if we apply torque, we cause changes to the object's rotation, therefore we cause an angular acceleration. Okay, so again, equivalent versus, right, so mass to linear to rotational, equivalency here. So Newton's second law of rotational motion tells us that when an external net torque is exerted on an object, the object undergoes an angular acceleration. So what do we say? The sum of the torques is equal to I times alpha. So again, right, I is the rotational equivalent of mass. Alpha is the rotational equivalent of acceleration. Torque is the rotational equivalent of force. So when you solve dynamics problems, you go back way back to Unit 2 when we talked about 3 simple steps in solving these problems, right? And they were draw, sum, solve. Now, it's going to look a little bit different now because when we drew them way back in Unit 2, we put the forces coming from the center of mass. Now, when you have an object that is rotating, you have to draw the free body diagram, and the forces have to be drawn where they're applied, because that is where the torque is applied, right? So in these problems, you are going to now have to probably include the pulley. So you can see I've got a little diagram here of an Atwood machine. This indicates that we have rotation, so this would be a rotational dynamics problem. So if we do our draw step, something you see is for the hanging blocks, they're going to be the same. But now you can see that we have, that's one. So you can see that our tensions may not be equal as it was way back when. So this would be M1G. Now, if the pulley rotates towards the right here, that means M2 is going to drop down. So my positive direction will be down here. For M1, that's going to move up. So my positive direction will be up. Okay, and now if I draw for M2, right, these are going to be more of our traditional looking free body diagram pieces. Okay, now we throw in the third step, right, the third piece, which is the pulley. Okay, so T2, right, is heading down. T1 is heading down this way. So T2 would cause a positive torque the way we're addressing this, and T1 would cause a negative torque. But again, just like, right, what are we looking for? Something that we can maybe solve for in terms of each other. Okay, so those tensions are going to be the same. So that would be our draw step, and then now you do the summing. So here you would sum the torques, right, and the forces. Okay, then I would write my vector sums like T1 minus M1G equals MA, T2 minus, or M2G minus T2 equals M1A or M2A, and then I handle the torque there in the middle. I'm not going to go too far into it because this is going to be, essentially part of our example problem. And then finally, just solve for what you're looking for. You may be looking for, so another big equation that's used here, right, would be A equals R alpha, because I would look for alpha in terms of A. So we have A over R, and I would substitute this anywhere I had an alpha, okay, because sometimes you look for a linear acceleration, Sometimes you may be looking for both the linear and angular acceleration. Sometimes you may be looking for the tension. Okay, so let's look at an example problem. So here we have a 5 kilogram mass attached to a string that's wound around a 0.8 kilogram disc. So the disc is going to help us because we know what the I for the disc is. All right, 1/2 mr squared. So that's going to be important. It has a radius of 0.012. When the mass is released, the linear acceleration of the mass, of what is the linear acceleration of the mass, the angular acceleration of the pulley, and the tension in the rope. Here it says draw separate force diagrams for the pulley and the mass. Right? And so here's my mass. I would have mg, tension up. So if I let this rotate, it's going to accelerate to the right here, so clockwise, and then the mass will accelerate down. So if I draw my free body diagram for my mass, or for my pulley, the only force acting is tension. Okay, but again, these two are equal. All right, and so if I can find T in one equation, then I can substitute it back into the other equation. So let's do mg minus T equals ma. So there's the sum of my forces. Now I sum my torque, so I have one torque. So I would have tau tension is equal to I alpha. Now I'm going to take 1/2 mr squared, plug it in there. Here's what I'm going to plug in A over R, right? Because I have an A here, I have an A here. Well, guess what? The pulley accelerates linearly with the same magnitude as the one it's with the block. And so I know that this is going to be R sub T, or we'll just call it big R because that's what they call it in our diagram. So we're going to have big R times tension equals 1/2 big M R squared times A over big R. Right? And so this may look complicated because I have tensions, I have masses, right? I have big M, small m, but understand this R here cancels one of these R's. The other R is taken up by the one across the equal sign there. And so what do I end up with? A simple equation that says tension equals 1/2 big M times A. Well, now I can take that and, went a little too far with my arrow. All right, so I can take that now and plug it in for that T and solve for A. So we do mg minus 1/2 big MA equals little m times A. So I'm going to add the 1/2 big MA over. Okay, now so I have mg equals, I'm going to do a little factoring here. So I have little m plus 1/2 big M. And so acceleration, now remember when we talked about additive machines, we're going to divide by total mass. So this is kind of a total mass, but note that because of the disk, really it's only going to be focusing on half of that mass, but it's still total mass in some way of that system. So A, right, our acceleration is going to be mg divided by little m plus 1/2 times big M. And so now I can substitute in my values. So I have 5 times 9.81 or 10 times, or divided by 5 plus 1/2 times 0.8. Okay, and so my acceleration, my linear acceleration is going to be equal to, drum roll please, 9.07 meters per second squared. Okay, so now there's my linear acceleration. Now I can find my alpha by doing A divided by R. Right, and so I'm going to do 9.07 divided by 0.012. Now you do have to be careful because sometimes they'll try to trick you and say, hey, the diameter is this, but you need the radius. Okay, and so that alpha is going to be 756 radians per second squared. And now the last thing I need to calculate is the tension. And I just simply do tension is 1/2 big M times A. I can substitute in stuff here to get my tension, but I already have a formula for tension. So let's just use that. So 1/2 times, now this is of the pulley, 0.8 times 9.07, and it's going to give me a tension of 3.63 newtons. So there's my tension, here's my alpha, and then here's my acceleration. Okay, so this kind of puts an end to the rotational dynamics topic, right? The next topic that we're going to look at is we're going to revisit conservation laws. Okay, so remember in mechanics we've talked about that there's 3 of them. Now we're going to discuss that third one.